Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the chapter 1 of electrical machines subject. Okay, so today we will discuss in this chapter about transformers. So starting from the ideal transformer, then we will discuss about the practical single phase transformer, then we will understand the losses in a transformer, the construction of a transformer, the efficiency of a transformer, the voltage regulation of a single phase transformer. Then we will discuss auto transformer, three phase transformer, and there are infinite things, right? We will discuss. So we will cover everything comprehensively. So make sure to follow this playlist completely and listen to every word that I say, because every word is important. Trust me, whatever is present in the notes and whatever I say is everything is important. So one request from my end, basically this playlist completely will be free. So my request would be, if you are enjoying the concept, please do comment down below on this video and on the first few videos of the playlist. That will really help us out, and that really keeps us motivated to bring more content like this. And trust me, you will love this. Okay, whatever I am discussing, you will love this. So I think you have already watched the marathon, chapter 0 marathon. So there I gave you a bit of overview about transformers, but mainly we discussed about ideal transformers, right? There we just did not discuss about practical transformers. So of course that was a common portion for WEC and IN. That's why we had to only limit our knowledge within the idealities, because they will obviously not study non-ideal transformer, right? So that's why I limited whatever I discussed, that was for ideal transformer. Now we will come here and we will discuss about non-ideal transformer as well. But before, obviously, today will be the lecture 7. So today we will mainly discuss about ideal transformer only. So first few lectures we will again discuss about ideal transformer only. Few more things about ideal transformer. Okay, we will discuss about induced EMF. I know in chapter 0 also we have discussed about this. Briefly we will discuss, and also we will draw the phasor diagram in an ideal transformer. So basic thing we have already discussed in the chapter 0, that if I have a two windings which have different turns N1 and 2, and if I apply a time varying voltage here, due to the time varying voltage a time varying current will flow, due to the time varying current a time varying flux will flow. Okay, and whenever there is a time varying flux, what happens? There is a induced voltage, there is an induced EMF both in the secondary of the coil and the of course in the primary of the coil. There will be an induced EMF if there is a time varying flux that will actually oppose its initial cause. So that is what we will discuss. So transformer is what actually? Transformer is an electrical device that transfers AC power. Remember, we mainly transfer AC power, we will not be able to transfer DC power. Why? Because for DC, right, this d phi by dt is 0, right? Why? Because there is no change in flux, because current is constant. If current is constant, then flux also will be constant. If flux is constant, then there is no change in the voltage. That means there is like no magnetic connection between here and here, right? Yes, a flux will flow, a flux will actually flow through this core, that is totally correct, but that flux will not induce any EMF here. Okay, that flux will not induce any EMF here, because the d phi by dt is simply 0. Okay, so that's why we use transformer to transfer AC power. And of course everywhere you see in your home, the power that comes to you through the distribution transformers. So from one voltage level to another voltage level through electromagnetic induction. So what do you mean by voltage level? So already like we have discussed this in the chapter 0 as well, that if I apply a sinusoidal voltage here, and let's assume that this voltage is Vm sin omega t, Vm1 sin omega t. Okay, so if this is the voltage, then I can easily find out the flux. So I know the voltage, this is the voltage across this coil, right? And this coil is just like an inductor. So I know V1 will be equals to N, like I know there will be an induced EMF, right? That is E1. So E1 will be equals to, due to the time varying flux and all those things, there will be an induced EMF. So E1 will be equals to uh, some minus of N d phi by dt. Now for a second, just ignore the negative sign. Okay, I'm just talking about the magnitude. Negative sign just signifies like when will the flux, when will the voltage increase or decrease. Okay, just ignore the negative sign for now. So here what we can discuss is that my if I write what is E1 actually, so E1 and V1 are connected in parallel. So this will be equals to V1. So I'm going in the opposite direction now. So main thing is yes, we know that due to some like sinusoidal voltage, a sinusoidal current will be formed. Due to the sinusoidal current, a sinusoidal sinusoidal flux will be formed. Due to the flux, an induced EMF will be there. But I am going actually in the backwards direction. Okay, what I am telling that yes, there is induced EMF here, and as things are connected in parallel, so I will equate this equation. I mean, I will equate this. So E1 will be equals to V1 because this is in parallel. Will be equals to, just ignoring the negative sign for now, n d phi dt. Okay, of course you can take the negative sign as well. I know you will have the confusion. Let's take the negative sign, no problems. So now what we can comment is that if I know my v1, what is my v1? V1 is this, right? Vm1 sine omega t. So v1 is this, vm1 sine omega t. So if I just write the values, that it is vm1 sine omega t equals to minus n d phi by dt. Minus n n1 d phi by dt. So from here I can easily find out what will be my d phi by dt, what will be my phi of t, right? So my phi of t, if I integrate this thing, this will be vm1 by n omega into cos of omega t, or my phi of t, this is phi of t, right? Instantaneous value, phi of t will be equals to vm1 divided by 2 pi f n1. Sorry, this will be n1, right? I forgot, this will be n1. So n1 into cos of omega t. So from here, right, we can directly say like what will be the this peak value. So my peak value of flux, or this is my phi of t. So this phi of t will actually flow through this whole core. This phi of t will actually flow through this whole core, right? So now if I connect a secondary winding as well, it will have an induced EMF, right? So that is what is written over here. So a magnetic circuit consists of a core material with coil wound around it. So a single coil is excited. This V1 is the RMS value. So for now our assumption is this coil, right, does not have any resistance. So any wire will have a resistance. So for now our assumption is this coil does not have any resistance. There is no leakage flux. We'll discuss about what is leakage flux later on. So from here this phi of t is totally flowing. So from here I can directly say like this. Also we have discussed previously as well, just revising again. So from here my phi max will be, this is vrms, right? So this is root 2 into vrms. So this will be v1 rms divided by root 2 pi f n1. Okay, this will be my maximum peak value of flux. Okay, so I hope you have understood this point. So like we had actually already assumed this, because I already said to you initially that my e1 and v1 are same. How are e1 and v1 are same? So if we actually, in reality what happens is there is actually winding resistance. So then my v1 and e1 are not equal. So that also we will discuss, but for now there is no winding resistance. So directly I can write that my whatever induced voltage is the same as the supply voltage only. Okay, got this point? So this we already had discussed, right? This we already had discussed. So like in DC circuits, what happens? We have this constant current that produces a MMF, and due to that, the flux, right? Like the flux is directly dependent on the current and the number of turns. Okay, but in this case, it is dependent on the, it is directly peak value of the flux is dependent on V1 and F. Okay, not on the permeability. So if we see, there is no material dependency. So the peak value is not dependent on the permeability. Okay, peak value of the flux is not dependent on the permeability. But in DC circuits, it was MMF by reluctance. So reluctance depends on permeability. if the core material is replaced with another having different permeability, the peak flux remains unchanged as long as the applied voltage and frequency remain constant. So the peak value of the flux will not change, but still we want a like good permeability material. We will discuss about that later on, why we still require a good permeability material. We will discuss about that. Okay, so this you have already understood that what happens when a voltage source is applied across a coil. Okay, so let's go through this again. If a ammeter is there, so I will apply a voltage source, and due to this voltage source, what will happen? A flux will get generated, correct? A flux. So what happens as soon as I apply a voltage source, like AC voltage source, due to this, right, a flux gets generated in the coil. Okay, like actually internally what is happening? Flux is getting generated. So if a flux is getting generated, then of course the flux density is getting generated. If flux density is there, then there will be some magnetic field intensity. So basically, if you remember, I have my BH curve, right? This we discussed previously as well. If you remember that, let's say for a normal material, this is my BH curve. So if I have flux, okay, then I will have the magnetic field intensity. So this ammeter will measure, like all these things will happen in sequence. So this is the sequence actually. If someone asks you in interview, like what happens actually, so initially I apply a voltage. If I apply a voltage, a flux gets generated in the coil. Okay, because it is a time varying voltage, that's why a flux gets generated. So due to that, I have a peak flux density, and due to flux density, of course, if there is a flux density, there will be a magnetizing force. So this is my flux magnetic intensity, and my magnetic intensity is proportional or equals to Ni divided by L, if you remember, right, using the Ampere's law. So from here you can find out, like this is my B max. Let's assume like I have some phi max. According to phi max I will get some B max. According to B max I will get some H max. So I got my H max, and H max will be equals to N into I max divided by L. And like let's say, like if someone asks you what will be the ammeter reading, how do you find out the ammeter reading, right? So this is how you find out. So you find out H, and H max is N I like I max is what? I max is H max into L divided by N. Okay, N1, or in the primary side, if it is, it will be N1. So from here I can directly, like what will the ammeter read? So any measuring device in AC always reads the RMS value. So ammeter will read IRMS will be equals to H max into L divided by root 2 into N1. Okay, so like if someone asks you how can you find out the RMS value of the current if secondary is not there. So currently I am not discussing about the secondary, right, or the coil 2. I'm just discussing if a single coil is there, how will you find out the RMS value of current? Okay, like all these things you can use. All these things you can use. Okay, whatever I discuss, the same thing is written over here. Okay, now let's discuss when there is a like okay, whatever we discussed, the same thing is written over here only. So same V1 will be this, phi max will be this. From there you can totally find out the values. Okay, and how do you calculate? Like I'm just telling you how will you calculate the values of current and all those things, flux density. Okay, so from what this is my I max. So my IRMS I had already discussed. IRMS will be H max dot L dot root 2 N1. Okay, so like this you can find out. And in the previous lecture, I forgot if I mentioned or not in chapter 0 that this is my BH curve, and in the BH curve the slope, right, slope actually represents the permeability. Slope represents the permeability. Okay, if you remember that my B is equals to mu into H, right? B is equals to mu into H. So if I just do dB upon dH, that will give me E mu only. So that is the slope basically. Slope of this graph will give me the permeability. Okay, same as y equals to mx. Okay, now if I keep on changing the material, what will happen? What will happen actually? If I keep on changing the material, what will happen? So if I keep on changing the material, if let's say I'm choosing a better material, okay, whatever material I have, I'm choosing a better material. How will I choose the better material? So better material means the permeability will be very high, that it will permit all the magnetic field, all the flux lines, right? In the chapter 0 we had discussed about this permeability concept. So better materials means, like whatever we're discussing about magnetic circuits. So better means that it should permit all the flux lines, magnetic field lines. So my mu r should be infinity, tending towards infinity. So that is my main target, right? So like ideally I would want my mu r to be infinity, so that I am able to pass all the magnetic flux. Okay, if permeability is infinity, so there will not be any problem at all, there won't be any problem at all, right? So my target is that I make the permeability maximum. Okay, that is my target. Why is it important? I will tell you why is it important. Although you might have a question that, sir, you told, right, you told here that if my voltage is fixed, if my voltage is fixed and my frequency is fixed, then my maximum flux value is also fixed. Yes, you are correct. But current is not fixed, right? So if current for some reason is here very low, that will be a problem. We will understand that later on. Okay, so I would want my permeability to be as high as possible. So which side this graph will go move? Okay, pause the video and tell me that if I am increasing my permeability, will my graph go here or here? So permeability is what? Permeability is the slope of this graph. So if I measure the slope here, it is what? It is more higher, right? It is more higher. If I measure the slope here, it is going towards parallel to the x-axis, that is slope is 0, right? Almost 0. Okay. Of course, if I keep on increasing on the top side, that means the slope is increasing. So of course, my graph will go on the top side. Okay. So I will like go like this and go like this. So what is the difference here? So the difference is basically, although the voltage, like the flux is independent of the sorry, like I had to drink a bit of water. So what I was saying is, although just hold on, I will just do one thing. This lecture, although the voltage is fixed, if voltage is fixed, okay, if voltage is fixed, then flux is fixed, correct? Of course, if voltage and frequency are fixed, then flux is fixed. Then what is the problem? Why do I want a higher permeability? Why would I want a higher permeability? The difference lies in the current. So to pass the same amount of flux, right? To pass the same amount of flux, for the first case, if I observe here, okay, this H is proportional to the current only, right? So in the first case, this is proportional to, let's say, I1, and in the second case, let's take okay, not this graph, sorry, not this graph. Let's take this like dark yellow graph. So here I'm cutting the graph, right, for Bmax. So this is the amount of flux that I need to pass. So for the same amount of flux, if I measure the current, right, so this will be what? I2. So tell me, is I1 bigger or I2 bigger? Is I1 bigger or I2 bigger? So of course you will say, sir, I1 is bigger than I2. So if I1 is bigger than I2, so if I multiply by voltage V1 is fixed, right? I know it's AC quantity, just we are multiplying, that's it. Okay, I know it's AC quantity. So V1 into I1 will be greater than V1 into I2. So this is what? Power, right? Power. So in the first case, I need more power than the second case. So if I have a better material, okay, then I will need lower amount of power to pass the same amount of flux. Although the voltage, if voltage is fixed, phi max is fixed, yes, that is correct, but current is not fixed, right? Current is not fixed. So we need to supply more current to pass the same amount of flux. So that is a problem. That is a problem. That's why we want our materials to be as good as possible. That is, the permeability to be as high as possible, as close to infinity as possible. Okay. So if you see here, right, this is like a graph of a material whose permeability is infinity. Basically, I don't need any current to pass flux, right? Even if I don't apply any current, automatically flux will get generated. Of course, that is not possible in real life. In real life, that is not possible, right? But uh, if you understand this ideal characteristics, then you will be able to understand the practical one. Okay, so this is the ideal one where mu r is infinity. Okay, we don't need any current to generate amount of flux. Okay, so I hope you have understood the thing. So my phi max is peak value of my flux is independent independent of material. Phi max is independent of material, no problem. But the current, right? Current is dependent, right? Current is dependent, and we want to minimize the amount of energy required. Okay, so we want to minimize our I max. Now remember, this I max is not the I max that will flow to your load. No, not that. This is the actually this is called as the magnetizing current. This we will learn later on as well. This is called as the magnetizing current. The amount of current that is required to magnetize the core. The lower, the better, because I don't want to waste my energy on magnetizing the core. I want to use as much of my energy on supplying the load, not on other things, not on other things. Okay. So this was about the magnetizing current. Now let's understand one more concept. If you have seen a BH curve in the chapter 0 as well, I hope we have discussed about this BH curve. Okay. So there, if you remember that we have many points like this: saturation, residual flux, coercivity. Okay, all these points are there actually. So now, if let's say like I will apply a voltage and sinusoidal voltage. So I will apply a sinusoidal voltage. I will apply a sinusoidal voltage. Voltage will be some sinusoidal. Okay. So my current also will be some sinusoidal, right? Current also will be some sinusoidal. Now, if the core material has this kind of saturation, right? This kind of BH curve, what can be the problem? So if my current is actually higher, okay, if my current value is very high, what will happen? The flux will not be purely sinusoidal. Why? Because let's say my current is sinusoidal, right? So my current is sinusoidal, and I know like this is my graph. So my current is actually proportional to the magnetizing force or magnetic field intensity, right? So if current is increasing, magnetizing force will increase. So let's say this is the point. Let's assume this is the point for some current equals to 1 ampere, right? Any random point. So for this current equals to 1 ampere, what will be the flux? So the flux, right, will be this value. Okay. So although you might have a bit of doubt that how like there are two curves, right? Which one will I choose? So generally, what happens if we are just magnetizing the core, that means we are just magnetizing. So we will choose this first core. Once we have reached the peak, then we are demagnetizing. Then we will choose this second curve. Okay. It is just how the BH curve works. All this I have discussed in the material properties in the chapter 0. So I hope you have understood that. Okay. So initially I am magnetizing, so I'll choose this curve 1 only. Okay. So now let's assume that my current magnitude increases very large, right? Let's assume this has increased to 3, like peak amplitude is 3 ampere. But my, like, what happens after this, right? After this point, what happens? My core basically saturates. So if I keep on increasing my current, that is, if I keep on increasing my magnetizing force, the flux density will not actually increase. So that is an inherent property of magnetic elements, that there is a saturation. Saturation means I keep on increasing my current, my flux won't increase. Just if you remember, if I have a resistor here, okay, and there is a voltage source, let's say V. If I keep on increasing this V, I will increase, right? I will keep on increasing, no problem. But in real life, you know that you actually will not be able to do it. Why? Because you go to the market, whenever you go to the market, you say, I need a 1 ohm resistor. The first question the what do you call it, shopkeeper will ask you is, what is the wattage rating of the resistor that you want? Because 1 ohm resistor are many, there are many 1 ohm resistors, but each resistor, like one of them will have 0.25 watts of rating, one of them will have 0.5 watts of rating, one of them will have 10 watts of rating. What does this voltage signify? This voltage signify the maximum current that the resistor can take. After this, the resistor simply will get damaged. It will just burn out, it will damage. So no current will flow basically. Something similar here as well, although here core will not get damaged, but saturation will happen. I keep on increasing my I, the flux will not increase actually, as the core has saturated. So what happens, let's say I am at this position, the problem will be that what will my flux graph look like? So my flux graph, if I plot my graph of the flux, right? All this I am talking without the secondary connected, just we are in the primary zone only. Okay, so omega is here, this is my phi of t. So initially as I am increasing my current, my flux is increasing. So this region actually, this region, right, this kind of region, okay, this kind of region is known as the linear region. This kind of region is known as the linear region. Okay, so in linear region, if I keep on increasing my current, the flux will also increase. Flux density increases, so area is constant, so flux will also increase. So in this region, I keep on increasing my current, so flux is increasing. This is not omega, this is t. Okay, this is simply graph with respect to t. This is also with respect to t only. But what happens as I reach this position or near about this higher position, right? I keep on increasing my current, but the flux does not increase actually, because it has saturated. It has saturated, so flux density is constant. It does not matter whatever the value of current is, the flux density is constant. So flux density will be constant here. Okay, then after a certain while, again I come back here. So if I again plot the graph, I will choose the curve 2 now. If I choose the curve 2, because I am demagnetizing, so as I am demagnetizing, I am lying here. So now of course the flux will reduce from this saturation, it will reduce, so flux will reduce, and again I am in the linear region, so it will reduce according to the current. So same thing will happen in the other half as well, in the negative half as well, right? So again same thing will happen, that again it will, core will saturate in the negative direction, and again it will keep on repeating this pattern. Okay, it will just keep on repeating this pattern, that's it. So the important point is basically what is happening, although I was giving a sinusoidal current, because I was giving a sinusoidal voltage, I am getting a, this kind of waveform is called flat topped waveform. Okay, it is not sinusoidal. Flat top, why? Because the top is flat basically, the top side is flat, that's why it is called flat top. So in this waveform, right, now in the next stage what we will do is, of course, you know, in a transformer I don't have just the primary, I have a secondary. So this flux links the secondary, and we differentiate that flux to get the induced voltage of the secondary. So if it is not purely sinusoidal, and if I differentiate this, right, I will actually not get, the induced voltage will not be sinusoidal. The induced voltage will not be sinusoidal. Okay, induced voltage in secondary will not be sinusoidal. And if it is not sinusoidal, that means what? That means basically it contains harmonics. So we will discuss about harmonics as well. Harmonics means any unwanted signals, right? Unwanted signals. What is unwanted? So this is unwanted, right? I did not want this portion. What I wanted was this kind of something like this, right? Something like this. But this is totally unwanted, right? So you will study in signals what is harmonics and all those things. Machines also will discuss later on. We'll discuss. Okay. So this is actually not a good thing, right? This is actually not a good thing. Correct. So we want a way such that the saturation actually comes very late, right? Like our whatever the maximum current that we will use, it should lie within the linear region. It should lie within the linear region. It should not lie, it should not go beyond the saturation. Then there will be a problem. Okay, so that is the main point that you need to understand. Now in these kind of cases, let's say you want to design a transformer, you don't care about the like magnetizing current, right? Whatever current is required, I will give that amount of current. What do you care? You care about the just the waveform should be pure. Whatever waveform I am sending in the input, it should reach the output. So in those kind of cases, these kind of BH curve is the best. Okay, so this BH curve is not good actually. This is known as the hysteresis loop, right? So in those kind of cases, if my BH curve is totally linear, linear meaning like this. Okay, if it is totally linear, that means my permeability will be constant. Yes, I will have a finite permeability will be constant, some value. Okay, almost equals to 1 or something low. But due to the linear nature, as I increase my current, the flux also will increase. Basically it is directly proportional. So flux is directly proportional to the current. So my waveform is not distorted anymore. So these kind of characteristics is present in air. Okay, so you might have a doubt, sir, why don't we use this, why don't we use air? Okay, so we will use air as a transformer core. We will use air as transformer core when linearity needs to be maintained, or we need to reduce noise. So noise, harmonics, all those things, reduce harmonics, noise. So then we will use air cored transformer. If you have heard something like this, air cored transformer, right? Those kind of transformers are the transformers in which there is very little noise, no harmonics. But what is the problem? The problem is that I will require more magnetizing current, right? Because generally what happens, air mu r is approximately equals to 1. If it is approximately equals to 1, my magnetizing current will be very high. So my power loss will be very high. Okay, to pass the same amount of flux, the magnetizing current will be very high. So the uh, basically the problem is it will consume more power, right? So that is the problem. It will consume more power. We, of course, we don't want to waste too much power in generating the magnetic field itself. Okay, got it? Understood? So this is the like I am telling you practical things as well, because in the interview you might get asked why we sometimes use air core transformer if its permeability is bad. Okay, or why don't we use air core transformer? So all these things, knowing all these things is actually important. Okay, now let's discuss one more concept. Okay, this was about the flux. Now let's discuss about the AC plus DC. If in the transformer, okay, if in the transformer I have the transformer, I'm just talking about a single winding right now. I'm not even talking about like two winding transformer. Just we are discussing about single winding only. Okay, so if I have a transformer here, okay, and this transformer, where did it go? This transformer has both AC plus DC. So right now what we will discuss is this transformer will have both AC plus DC. So it is why transformer does not work in DC. So this, right, we have bit of it we have discussed in like chapter 0 as well, but there we assume transformer to be inductor because it was totally ideal. But let's say I'm giving AC plus DC. Now what will happen? So if I'm giving AC plus DC, that means this will be some voltage V1 with frequency F, and this will be some VDC. Okay, let's assume this is some VDC. So I'm applying both VDC and V1. What will be the problem here? So if I bring back the same curve, right, I will bring back the same curve, and instead of using a like a difficult BH curve, what I will use a normal BH curve only. This hysteresis loop may be a bit confusing to you. I will use a normal BH curve. Okay, so if I bring it back here, so this will be a normal curve. So normal curve is somewhat like this. Normal curve would be somewhat like this. Okay, after this it saturates. Now, if I have actually applied a DC, my current, right? Current will have two components, AC and DC. So current will be shifted now. Current will be shifted somewhere here. Okay. So if current is shifted somewhere here, what is the problem? The problem is already my already like this current is combination of both DC and AC. Correct. This current will be a combination of DC and AC. So this current is combination of both DC and AC. Let's assume this current is 2 amperes DC and it is like Im sin omega t. So 1 sin omega t. So I'm here. So already, right? Already if you see, if I plot these points, the change in the current is not getting represented in change in flux, because if I keep on changing my current, flux is constant. Flux does not change. So the flux, right, is just flux waveform will be just weird. Flux waveform will be just weird. Okay, so initially there it will show some change, then it will be just constant, and then again if I keep on reducing for a while it will be constant, then again it will just reduce by a very small amount. Okay, and here it will be like this, like because this region is totally in the linear region. This region is totally in the linear region. So my this flux waveform is so bad. It is not even a sinusoidal. What is this? This is not a sinusoidal, right? This is something else, right? So many harmonics are there. So basically, most of the time, transformer works in saturation. Transformer works in saturation most of the time. Okay, so it is not that simple to analyze. So whenever DC sources are present, right? Whenever DC sources are present, you analyze the circuit with fundamentals. You don't use formulae. What formulae? This age old formula, E1 by E2 equals to N1 by N2. Don't use that. Okay, don't use that. Just be look at the circuit and try to analyze it, because of course in real life we will never apply DC. The reason I will tell once we will study the practical transformer, I will tell why we don't apply DC. So this I have already discussed that yes, windings will get burnt. How it will get burnt, that also I will discuss. Okay, so in real life we will never apply DC, but in interview or in some place in question they might ask this. Okay, so that was about the DC. Now this is the theoretical limit. There is the infinite permeability. If the core material had extremely high permeability, the BH curve will be vertical. That we have already discussed. That means basically my magnetizing current, the to establish the required flux, how much current do I need? Zero, negligible current, zero current, right? I don't need any current to establish the whatever flux that is required. Okay, but in practical applications, materials with high permeability like silicon, steel or ferrite cores are used. Of course, infinite permeability is not possible, so we use like materials with high permeability like silicon, steel or ferrite cores. This significantly reduces the magnetizing current and it improves the energy efficiently. Okay, improves the energy efficiency because of course the power required will be less, right? So P core, this is known as the core loss that I will discuss when we will discuss about core losses, when we will discuss about the losses in transformer. So P core will be simply very low. Now like why is transformer so essential, right? This is the first chapter of machines, and in the first chapter we are studying about transformer. Why is it so important? It is important because in early days of electrical power distribution, if you have studied a bit of history about current and transformer, Thomas Edison developed a 120 volt DC system for incandescent lighting. Okay, however DC power suffered from high transmission losses, so there were huge losses in the transmission lines, right? Because like losses is very high because the constant current is flowing through the resistor, but in AC it is RMS current, right? So losses gets reduced due to excessive current flow, requiring generating stations every blocks to minimize the voltage drop. Okay, thus the invention of AC power came. So AC power was generated at a central power plant at voltages 12 kilovolt to 25 kilovolt. So at low voltages, this kilovolt seems like a high voltage, but reality it is low voltage only. But then what we do, we step up the voltage. If I step up the voltage to 110 kilovolt to 100 volt, so ultimately what we want to do, we want to transmit power. So let's say I want to transmit 1 kilowatt of power. So there are two ways to transmit 1 kilowatt of power. So either what you can do, you can make the voltage 100 volts. So how much current I need to transfer? So just talking about RMS values here, okay? Just rough calculations. I know things are easy here. It is not that simple, voltage into current, but just a rough calculation I'm telling you, okay? So what is the current? If the 100 volt is fixed, it is 10 amperes. If let's say the same thing I would have transferred in 1 kilo volt, right? Then how much current would I need? I need only 1 ampere of current. How are the losses calculated? Losses are always calculated as I square into R. So this is my line. So this is my sender and this is my receiver. So this is my sender and this is my receiver, right? So I am transmitting power from here to here. So here from here to here, some current is flowing. Some current is flowing, right? So if some current is flowing, that means basically this will be what? This will be the I square R. So here the I has reduced, but here the I is very large, right? In DC, it is not that easy to step down or step up the voltage, okay? Not that simple. But in AC, with the invention of transformer, we were able to easily step up or step down the voltage. That's why we transmit our power in AC only, okay? That's why transformer is very very important and integral part of power transmission everywhere, okay? So transformers have many applications like voltage regulation. It is used as step up transformer, step down transformer, okay? Impedance matching as well, because like this we will learn later on, that let's say I have this like we want to, this is my resistance and this is my RL, okay? This is some RS source resistance, and here I have some supply, right? Some supply I have. So I want to transfer the maximum amount of power to this. How will I transfer the maximum amount of power? Sometimes what we do is, instead of directly connecting this resistor, right, what we do, we have a transformer here. Why we have this transformer? I will tell you why we have this transformer. I will tell you. So let's say this resistance is 100 ohms, okay, and this turns ratio is 10 is to 1, okay, although it does not seem like, it seems like the opposite. So I will draw the opposite one. So this will be, seems like 10 is to 1, okay? And the problem is that you actually, you don't have, like, if you want to transfer the maximum power through this 100 ohms, what do you need to do? You needed to actually connect a 100 ohm resistor here, okay? That is what was the requirement. But of course you don't have that, okay? You don't have that 100 ohms of resistance. So let's say by chance you have a transformer of this turns ratio and you have a 1 ohm of resistor, 1 ohm resistor. If you have a 1 ohm resistor, then you can actually connect it to the secondary of this transformer, and from the primary of the transformer it will seem like it is 100 ohms. How is it possible? So if I refer this resistance to the primary, it will be 1 into 10 by 1 whole square equals to 100 ohms. And you will say, sir, what are you doing? I'm not understanding anything. And because I have not explained to you, right, what is referring of sources, I'm just explaining the use cases of transformer. We have still yet to learn about this. In the next lecture only we will learn about this, okay? So like this impedance matching feature can be used. It is used in many other places as well. Isolation as well it is used. Why is it isolation? Because there is no between the primary, right, between the primary and the secondary winding. If I just if I copy this thing, that between the primary, although remember the picture is like this, that the windings are very further away from each other, but reality is very different. In real life, the windings are actually wound over one another. Okay, in picture it may seem like the one winding is one of the in one of the legs, other winding is in the other legs, but in reality both the windings are actually wound over each other only. There is a insulation, between the windings. Okay, but what do we mean by isolation? Isolation means there is electrical isolation. There is no connection between the primary winding and the secondary winding. Okay, it is totally isolated. So there is magnetic connection because the same magnetic flux flows through this winding 1 and winding 2, but there is no electrical connection. So if there is no electrical connection, sometimes it helps in fault, uh, like recovering from fault and all those things, if the two systems are electrically isolated. So if one of the system has faults, the other system may not cause like fault. Okay, to isolate the faults, we will discuss in power system regarding this. Okay, so transformer generally operates on the principle of mutual inductance. So all this we have already discussed, like how flux gets generated, all those things we have already discussed. Okay, so the role of magnetic material. So the better the magnetic material, the lower the magnetizing current, that is my mu r is very high. Mu r is very high. Okay, mu r, if I choose a mu r very high, then the magnetic material will be low. So in case of ideal transformer, the magnetic material that we will use will be extremely high permeability, which will be approaching infinity. Of course, it is not possible to get infinity, but which will be approaching infinity. So the magnetizing current required will be vanishingly small. So Im will be almost equals to 0. This has a significance. We will discuss about that. Okay, so same thing, whatever I have discussed is written over here. You can go and read through this. Okay, so what are the things that a ideal transformer should have? Okay, so I will add to this in the next lecture as well. I will add to this point in the next lecture as well. So for now, you can just understand that a ideal transformer should have zero winding resistance. It has no leakage flux. So I am applying a AC voltage source here. Okay, I'm applying a AC voltage source here. I'm applying a AC voltage source here. So due to this, some flux gets generated. Okay, due to this, some flux gets generated. So this flux actually links here as well. Now what will happen is, as this is the core. Okay, actually if you remember magnetic circuit, so air is also a magnetic material. It has mu r of 1. So what will happen here, right? Some of the flux that is coming out of here, it will actually, like a flux always try to close its path. So it will see air and it will see the core. So it is like a parallel path, right? So same like current, right? So if I have this current here, let's say 1 ampere, this is, let's say, 1 ohm, and this is 1000 ohm. Although yes, 1000 ohm is very large, so most of the current will flow through this 1 ohm only. Okay, you can calculate using current division rule. Most of the current will flow through this 1 ohm only, but some of the current will actually flow through this. Same thing is happening, is most of the flux will flow through the core only. That is what the core is meant for, but some of the flux will come out and complete the loop outside. Okay, and this kind of flux is known as the leakage flux. This we will not discuss for now. Of course, in an ideal transformer, we'll assume that there is no leakage flux. Okay, we will add this when we will discuss about practical transformer. So ideal transformer has these many things: infinite permeability, no leakage flux. Also few more things like the BH curve, right? BH curve will be totally, there will be no saturation, and of course the winding, there is no winding resistance, right? So that's why the voltage, supply voltage and the induced voltage will be same. Okay, so if all these things are met, then this is the voltage phi max expression we get, if all these conditions are met, and from there you will be able to find out your current and uh, RMS value of the currents and all those things. Okay, So now let's discuss about two winding transformer. If I have two winding transformer, what will happen in the secondary coil? So if I have two windings now, so of course all this is fixed, right? So this voltage will I will apply a voltage, so due to that a flux will flow, due to that a induced EMF will be there. Okay, so the flux value will be, this flux will be a time varying flux. Okay, due to this time varying flux, if you see, this phi of t actually flows through the winding 2 as well, right? Secondary winding. So this primary has, let's assume, has n1 number of turns and n2 number of turns in the secondary. So if I have a n2 number of turns in the secondary, and if there is change in flux, so according to Faraday's law, I know there will be a induced EMF. E2 will be equals to n2 d phi by dt, because flux is constant throughout the core, like flux is same towards the core. So the same flux is linking the primary and secondary. I know the induced EMF in the primary is what? N1 d phi by dt. So from here, like we already know the relation, that very basic relation, that my E1 by E2 will be equals to N1 by N2, and my E2 will be also what? E2 will be equals to the same equation that we have been studying for so long, root 2 pi f phi max, okay, into N2. This will be the induced voltage in the secondary. Now what about the sign? What about the sign? So sign also we have briefly discussed in the chapter 0 as well, that will I write this, if this is plus, right, will I write this as plus minus or minus plus? What will be the sign of E2? So for the sign of E2 we had already previously discussed, if you remember, that it should oppose its initial cause. What was its initial cause? What was the cause due to which the voltage got induced? So voltage got induced due to this flux. So I will oppose the flux. So I will generate, my aim is to generate a flux such that it opposes the initial flux. For that I have to assume the polarity. This also we have discussed previously as well. Some few things new we'll discuss. Don't worry, we will discuss few new things as well. Okay. So let me just delete this. Let me copy the previous one only. So here what we should do, I had taught you that we will use the dot polarity. So for a dot polarity, you assume a resistor value here, okay, and you assume a current basically. If I assume a current here, so this will be the voltage basically. If this is the current, right, so this is the direction of the current. So if I see that this is actually opposing the initial direction of the flux. So initial direction is downwards and this direction of the flux is opposing, right? Whatever the flux generated due to this induced current is opposing. So this will be plus and this will be minus. So my correct polarity. So these two will be dot, right? Or you can write this as a dot, these two as a dot. Basically, both should have the same polarity at certain instant of time. Okay, this we have already learned. So we want to like clear our concepts more. We want to clear our concepts even more. Okay, so here I have 4 configurations. Pause the video and try it out by yourself. Where will the dots be and plus minus be? Okay, this kind of exercise we have already done, right, in the lecture in the chapter 0 as well. So I will start basically. So if I start here, so for this kind of case, for the first one, if I show you for the first one, what is happening over here? So for the first one, this we have already done, right? This I guess we have already done, correct? So here I have a plus here and the winding orientation is like this. So if I place a dot over here, right, then there will be a dot here. Why? So the shortcut I have already told you, right, in the chapter 0. So you must watch the chapter 0. This shortcut I have already told you in chapter 0. Okay, so this, right, in circuit analysis, how do I write it? So circuit analysis, you write like something like this, that I have two coils. Okay, I'm not explaining how am I placing the two dots, not explaining this. Okay, so here I have a transformer, I have a dot here and I have a dot here. Okay, these two are the dot places. Now again, for this case, now this will always not work, this trick, right? Whatever I told you, that according to the winding orientation, if this winding is in front at the dot, then this also will be dot. This actually fails. Why this fails, that I will discuss. Okay, the basic trick, you know, right? What you do, you just assume a current here, and if I assume a current, the direction of the current will be something like this. That will be the opposing of the initial flux. Basics already you know. What about this one? So for this one, right, the orientation is, okay, not cut. the orientation is bit different. So if the orientation is bit different, what you will do, that if I assume a dot here, then this will be dot. Why this will be dot? According to the orientation. According to the orientation. So at a particular instant, if this node goes higher, this node will go higher in the same instant. Okay. So this will be dot. So if this is plus with the dot, this will be plus and minus. Okay. So current will go something like this. I2. Okay. And how do I? So there are many ways to write this. Either you can assume the positive side to be dot or the negative side. So negative side, if I assume to be dot, then right, this transformer can also be shown like this. Like it's totally up to you. Okay, does not matter. They just define the instantaneous polarity. So it will be like here I will have the dots. The dot is assigned to negative and the square is assigned to positive. So here dot is assigned to positive and here the dot is assigned to negative. Here as well. Here as well, the if I see, the dot is assigned to the positive and here dot is assigned here. Okay, N1 and or if I assign it to negative, so anything works, right? So I'm showing you all possibilities because in examination you should not get scared if something different comes up, right? So we can assume positive as dot, we can assume negative as dot, it does not matter, right? So here again positive is dot, here negative is dot. So if I assume negative to be dot, so then this point will be the dot and this point will be the dot. This will be the dot and this will be the dot. Okay, so that is the case over here, and for the others also you can, for these as well, my hope is you will be able to do it. Okay, so still I will do it because that's my task. So I will copy these things. Because these kind of questions will also come and you will not be able to solve it. Seems easy, very easy, but trust me, 90% of the students don't know this fundamental thing only. Okay, so you have already beaten 90% of the students. So now in this case again, if I assume a dot here, then what you observe is that flux direction will be again in this direction, that is in the downward direction. So I see this point is dot, that is in front of the core. So again in front of the core should be dot here. Okay, so again if I want to draw the circuit diagram, basically, because of course we will not every time draw the core, right? You should be comfortable with this representation. So the top is dot, here the bottom is dot, again same thing. So here as well this opposite. So or you can assume the negative to be dot and the negative to be dot here. Okay, and this, right? In this case, if I have a dot here, this will be dot here, right, outside the winding. So again both bottoms are dot. Either way works. Or both tops are dot. Okay, so basic thing, you know. One more thing I forgot to tell you about a three winding transformer. For multi winding transformer, right, this will not work. Three winding transformer we had already discussed, I think, previously. Now let's come back to our discussion, whatever we were discussing. So I was discussing that once we connect a load, so the secondary also a current will flow through this, right? Secondary a current will flow, this I2. A current in the secondary will flow. Okay, that is I2. And already current in the primary is flowing. What is that current? Initially, right, if this load was not connected, then I had to develop the flux phi, right, in the core. What was responsible for developing that flux? The magnetizing current Im. So initially, when no load, no load was there, then flux was developed due to the magnetizing current Im. So the current I1 was equals to Im only at no load. Okay. Now as soon as load has been connected to the secondary, as soon as load has been connected to the secondary, what is the problem? So initially what was the flux? Flux was phi m, right? Like let's assume peak flux was phi m, correct? In the core, the peak flux was phi m. Now as soon as a load is connected, so a current I2 will flow, and due to this current, like polarity, all those things we know, right? This is the polarity, this is plus minus, all these things we have already discussed. Okay, so if this current I2 flows, then this will also develop a what? MMF n into I2. This will develop a MMF, that is the magnitude is n into I2, correct? This is the MMF developed. Okay, this is the MMF developed. Sorry, N2 into I2, right? N2 into I2. Now due to this MMF, of course the flux in the core will be reduced, right? Because that is the main purpose of this MMF, right? That's why this MMF was actually created. Lenz law created this MMF. The net flux in the core gets reduced. What is the net flux now? Net flux is phi m minus this phi 2, right? Phi m minus this phi 2. Basically, flux also is proportional to the MMF only. Flux is proportional to MMF only, right? So net MMF on the core previously was N1 into Im, and now it has been reduced to N1 into Im minus N2 into I2. Now the thing is, this right, this winding will not allow it. This winding will not allow it. This initial winding will not allow, because initially phi m flux was flowing. So this winding will try to flow the same amount of flux, that is phi m. So it will again oppose this MMF. So it will create a additional MMF, that is N1 into I1, additional current known as I1 current. So it will create an additional current. Sometimes it is called I1 or it is called as I2 dash. It will create the additional current known as I2 dash to what? To nullify N2 into I2. So what is happening? Some opposing flux got produced here, opposing MMF. So of course we don't want opposing forces to win. So it generates an extra, it takes an additional current from the supply so that it can oppose the opposing flux, so that I can maintain the same amount of flux, that is phi m on the core. My purpose is I have to maintain the same amount of flux phi m on the core. Why? Because at the starting itself I have repeated 100 times that if voltage is fixed, if frequency is fixed, if number of turns is fixed, that means my phi m will be fixed. Haven't I repeated this 1000 times? Because I know you will have this confusion. Why sir? Why we will keep phi m fixed? This I have been repeating multiple times. Okay, if voltage is fixed, frequency is fixed, number of turns is fixed, then phi m will be fixed no matter what. Okay, so that's why we have to fix the flux in the core. So additionally we will generate extra MMF to nullify this. So ultimately my net MMF on the core should be always equals to N1 into Im. Okay, so it should be always equals to N1 into Im. So if it is always equals to N1 into Im, that means these two should be equals to 0 basically. So this will be N1 I2 dash will be equals to N2 I2. Okay, so from here I can directly write a very good equation, that is I2 upon I2 dash is equals to N1 upon N2. So this I2 dash is nothing but the, basically, right, what is my I2 dash? I2 dash is equals to, I2 dash is equals to N1 divided by, sorry, N2 divided by N1 into I2. Okay, so I2 dash is equals to N2 divided by N1 into I2. So this is also known as the reflected current. Reflected current of secondary, or in the winding loop, like secondary, naming it secondary is not actually totally correct. We will discuss about like what we actually name the windings. Okay, so from here actually roughly what happens, so my I1 current, right, is Im plus I2 dash additional current, correct? So generally what happens, Im current is very low, so I1 is roughly equals to I2 dash only. Okay, so basically my I1 over I2, because I1 is I2 dash, so I1 over I2 equals to N2 over N1, and very famous equation, and my E1, induced EMF upon induced EMF on the secondary, is equals to N1 by N2. So very famous equation, right? This you already know, very famous equation. So sometimes N1 by N2 is called as transformation ratio. You don't have to care about that. Okay, so one more key point is that, so what is the secondary voltage? Basically secondary voltage is what, this, right, I can further rewrite this as E1 by E2 is equals to I2 by I1, correct? If I see, because roughly, and if I assume my, there is no winding resistance, then whatever is the induced EMF, that will be the same as the load voltage and this primary voltage, because there is no winding resistance, there is no drop here. So this will be roughly equals to V1 over V2. Okay, so this I can rewrite as V1 over V2, because these two are equal, right? So I2 over I1 is N1 by N2, and V1 over V2 is also N1 by N2. So these two are equal. So from here I get a very, very important equation, that V1 into I1 is equals to V2 into I2. So basically this is V1 into V into I is simply volt ampere rating. So volt ampere of 1 is equals to volt ampere of second. So actually power, right, or energy, or KVA is conserved, or energy is conserved, right? So energy transformation does not happen. So this is approximately, because this we have assumed here. So whatever is the power in the primary side, same power will be in the secondary side, just the voltages will be transformed. So transformer is also known as a linear device. Okay, transformer is also known as a linear device. Why is it known as a linear device? Because if I just see one thing at one instant, that, let's say, if I see voltage, if I apply voltage V1 in the primary, in the secondary I get voltage V2, that is N N2 by N1 into V1, correct? So it is a linear ratio, this is a constant, right? So it is a linear ratio, my output voltage linearly depends on the input voltage. And if I see on the current by itself, so if I have applied a current V1, I2 will be what? I2 will be just the opposite, N1 by N2 into I1. So again it's like a constant multiplied by I1. So again it's a linear relation. Okay, so that's why the transformer is called as a linear device. Okay, don't look like if I'm applying a voltage here, so what will be the current? No, don't do that. Okay, if I'm applying a voltage, check the voltage. If I'm applying current, check the current in the output. Okay, so whatever we have discussed is written over here, like a flux will be generated, this will be the voltage ratio, all those things we have discussed, right? So basic, today we learned about the basic principle of transformers. So all this whatever we discuss is like if N2 is greater than N1, that means number of turns in the secondary is greater. That means E2 will be greater than E1 because the ratio must be same. So if E2 is greater, that means the secondary has more voltage than the primary. So it is called as a step up transformer. Okay, because we're increasing the voltage, and if N1 is greater than N2, it is called as step down because the N1 has more turns. So the secondary will have lower number of voltages. So although we don't actually say it like this, what we say is we define our windings as LV and HV windings. So N2, that is, and if N2 has more number of turns, then the winding 2 will be called as high voltage winding, because always the winding 2 will have high voltage because E1 by E2 is N1 by N2, correct? And winding 1 will be called as LV winding, okay, low voltage winding. That's it. So generally we don't call primary and secondary because there will be huge confusion, because the primary because the same transformer, let's say if I have a transformer here, 10:1 transformer, so the same transformer can be used as a step down transformer. So if I apply, let's say 100 volts here, AC, remember AC apply, so here I will get a 10 volt AC. Same transformer, if I apply a 100 volt here, I will get a 1000 volt AC here. It can be used as a step up or step down, right? Of course you need to lie in the rating. Okay, you cannot go beyond the rating. Whatever is the rated voltage here, you cannot go beyond that, else the device will get damaged. Because if I increase my voltage, 5 max will increase. So there is a limit, right? The core can take the maximum flux. After that, the core will simply saturate. Okay, so due to that confusion, what we do is we say like LV winding and HV winding. So LV winding means the low voltage winding, that means the winding that has lower number of turns, and HV windings means the high voltage winding, the winding that has higher number of turns. That's it. Okay, so yeah, that was basically it. So this famous equation is also written something like this. So it is 4.44, like you can remember this, but it takes hardly 10 seconds to derive. 4.44 F phi m into N2, and this will be 4.44 F into phi m into N1. Okay, so this is the like voltage in the coil 1 and coil 2. So basic things, I hope you have understood this. Okay, so few more points, like your power, right? Power conversion remains constant. Okay, power transfer, there is no power transfer actually. I mean, whatever power I will apply to the input, same power will be at the output. So in the winding 1 or in the LV winding, whatever power there will be, same power will be there in the HV winding. Whatever reactive power there will be in the LV winding, this is for a ideal transformer, right? For non-ideal, of course, there will be losses. I do understand that. For ideal transformer, there won't be any losses. So it will totally reflect to the secondary or the high voltage winding. Okay, but considering the losses, we will discuss. Okay, so whatever reactive power I will apply in the LV winding, same reactive power I will get back in the HV winding. Whatever apparent power, of course, if I apply in the complex apparent power, apply in the LV winding, same apparent power I will get in the HV winding. Okay, no problem. Another important key fact to note is that EMF per turn. So EMF per turn also is a very important term. So if you remember, this is the equation, right? This is the equation basically. So if I copy this, let me color this to white. So another important term is EMF per turn. So if you see that this is my E2 voltage, right, and same voltage E1 I am getting, just that the number of turns is changing, everything else is same, right? E1. So basically, right, if I write here that my E2 by N2 is equals to E1 by N1. So the EMF per turn in a transformer remains constant for ideal transformer, of course. So EMF per turn is constant. Okay, it will be same. If I know the EMF per turn of one of the windings, I will easily be able to find out the EMF per turn of the other windings. So these are the few like assumptions of a ideal transformer. So ideal transformer will have infinite permeability, zero pole loss, that is magnetizing current will be zero basically, zero leakage flux, zero winding resistance, linear magnetizing curve. There will be no saturation. Core does not saturate. Okay, no saturation basically. No saturation. Okay. So yeah, now let's briefly discuss about the phasor diagram. Briefly, let's discuss about the phasor diagram and we will wrap this lecture. Okay, I will give you a question as homework, and in the next lecture we will discuss. Okay, or let's discuss now itself the questions only. So first of all, let's discuss about the phasor diagram. This is phasor diagram of a ideal transformer. So if I see a ideal transformer, if I just see this winding in isolation, what am I seeing? I am observing that I am applying a voltage and this winding is just like acting as an inductor. So I am applying AC voltage across the inductor. Okay, flux I will discuss about flux. Okay, for now just see what am I actually doing. What am I actually doing? Okay, I am applying a voltage across a inductor basically. So what will be the phase relationship of the magnetizing current with respect to the voltage? So I know it is like a purely lagging circuit, right? So it is just a coil is just an inductor. So it is a purely lagging circuit. So I know the Im will lags V1 by 90 degree. This is the property of a inductive circuit. That's the property of an inductive circuit. So for now we are assuming that it is ideal. So only this inductance will be there, right? Which will be used for producing the magnetizing current. Okay. So my Im will always lag the voltage. So if my voltage is something sinusoidal, if V1 is something sinusoidal, right? Sin omega t. What will be Im current? So let's like again, if your AC is weak, you have to go and study the AC topic. We have discussed this very comprehensively over there. So this will be Im current, not Im current, sorry. This will be, let's say this is some sine function, right? Sorry, this is my cos function and my sine is here. And I am telling that my, like I lag the sine, right? I lag the sine. So if I lag the sine, because voltage is sine omega t, so lagging means going in the clockwise direction. So I'll go in this direction. So this will be here. So what is this? This is basically minus of cos omega t. So my flux, right, phi of t will be some phi m into minus of cos omega t. So not flux, sorry, not flux. My current. My current, magnetizing current, okay, it will be obviously AC quantity because everything is a AC quantity. It will be some Im, Imax, okay, into minus of cos omega t. Basically, it will be proportional to negative of cos omega t. Okay. So I know that basically my like my flux will be what? Flux will be proportional to the current only, because flux is mmf upon reluctance. So flux will be proportional to the current only. So this will be what? This will be basically equals to my phi of t will be some phi max into minus of cos omega t. So from here I can directly find out the induced EMF, right? Because I want to establish a relationship between the induced EMF and the flux and all those things. So flux will lag if current is lagging. So flux will also lag the voltage by 90 degrees. So if my voltage, let's assume my voltage is here. This is my reference. My voltage is here. Okay. V1 reference. So the magnetizing current also will lag here. Im, and the flux also will lag basically. So let me recolor the flux in a different manner. Flux also will lag. Okay, flux also lags and the magnetizing current also lags. So both of them lag basically. So now what we can say is we can like what where will this induced EMF be then? So my induced EMF is equals to what? So I will take into effect of the sign as well, right? So induced EMF E1 will be minus of N1 d phi dt. So it will be minus will be outside, N1 will be there. Differentiation of the flux. So it will be phi max is a constant. Cos omega t differentiation is minus sin omega t. So this will be minus sin omega t. Okay, just hold on. So minus cos omega t is there. Minus cos omega t differentiation will be plus sin omega t. Plus sin omega t. Okay. So this will be equals to basically this will be minus of N1 phi max. No, okay, sorry, omega also will be there, right? Because I'm differentiating with respect to t, so this will be omega also will be there. So basically this is what this is basically uh, 2 pi f 2 pi f phi max into N1 into sine of omega t. Minus sign is also there, right? So this I can take here minus sine of omega t. So basically, right, what is the phase relationship? It is minus of sine omega t. So if it is minus of sine omega t, if I assume my V1 to be reference here, then my sine will be somewhere here. Okay. Now don't get confused, please. I'm requesting you. I know you will be confused with one thing. I will tell you what is the confusion. The confusion is this is my E1, induced EMF E1. The confusion will be that you will say, sir, you are telling that E1 is just in phase opposition with V1. But here we have to satisfy KVL. KVL means that V1 and E1 will be same. Why are they not same? So this, right, this just represents the Lenz law. What does Lenz law say? Lenz law say that we will oppose the cause. Okay, that's it. Don't confuse with KVL and phasor. When you draw the phasor, you will show it like this only. Okay. When you write the KVL will be V1 will be equals to E1. Okay. Two things are different. Sometimes in few books you will see that they have drawn the E1 here as well. Okay. That is also fine. Just in most of the standard textbook, the E1 will be shown in the phase opposition. This just represents that we are opposing the voltage. Don't confuse yourself with this concept. Okay. KVL V1 is E1, that is fine. But here phasor E1 will be in phase opposition. Got it? Okay. That was the E1. What about E2? E2 will be same, right? Because E2 is what? E2 is N2 d phi by dt. So everything will be same, just N2 will be there. Right? This will be equals to 2 pi f phi max. N2 will be there, that's it. Here N2 will be there minus of sine omega t. Okay, minus of sine omega t. So yeah, E2 will be also in the same phase as E1 only, just the difference will be depending on the turns ratio. Depending on the turns ratio, whether it will be bigger than E1 or E2, that depends, right? Depending on the turns ratio. Let's assume that here in this case my N2 is greater than N1, so of course E2 voltage will be greater than E1. Okay, that is just the assumption. Okay, so this was basically phasor diagram of a totally ideal transformer. Okay, of course, as we move along we will discuss about non-identities as well. So now what we can do is they have told us that which of the following options represents possible voltage polarities in a single phase two winding transformer. Here Vp is the applied primary voltage, Ep is the induced voltage, Vs is the secondary open circuit secondary voltage, Vs, and Es is the induced secondary voltage. Okay, and the dots are given. So if you try to match, right, if you try to match that, like what was our shortcut? The shortcut was like if dot is with the inside the core, I mean the coil which is going inside the core, so here also dot should be with the inside only. So this is not possible, this combination not possible. This is here outside the core, dot is with the winding that is outside the core, and here dot is with the winding that is inside the core, not possible. Here dot is with the winding that is inside the core, here dot is with the winding that is outside the core, again not possible. Here also same thing, right, not possible. Okay, here also same thing, not possible. So actually in the examination what happened, this question came as MTA. Okay, this question actually was MTA. So anyone can do mistake. Okay, even IT professors, they are very knowledgeable, and of course they are very knowledgeable, that's why they are there, right? That's why they are IT professors. So but of course mistakes can happen. Okay, mistakes can happen, and it was a mistake on their end that they use this notation wrong. So don't be stressed in the examination hall that if you're not able to solve the question and you know the concept very well, right? Because I have taught you the concept very well and you're not able to solve it, you might feel like what is going wrong, and you waste your time. So don't waste your time in a particular question, move on from that question. Okay, so like how we could have improved this question was, instead of placing one dot here, one dot here, this would have been a possible combination, this would have been a correct combination, and this also would have been a correct combination, that if both the dots are with the winding that is outside the core or that is going inside the core, I mean on the behind the core, not in front of the core, behind the core, then that is a possible combination of the dot, this is a possible combination. So this question could have been made correct if the one of the dot would have been bottom or the other dot would have been top, then the question would have been simply correct. Okay, so yeah, let's solve this question. So this question we have, for the system shown in the figure, the phase relation of the current I with respect to the voltage V in is 1. Okay, so they are asking what is the phase relationship of the current I with respect to the voltage V in. So whatever phasor concepts we had learned, we will use that actually. Okay, we'll actually use that. So what we know is that this dot is here, this dot is here. So my, if this is my plus, right, if this is my plus minus, this will be my plus minus here. Okay, so it will just be a scaled version here, right? So this will be basically let's assume any turns ratio, right? Let's assume here n1 n2 turns. Okay, so this value will be n2 divided by n1, v2 divided by v1 equals to, yeah, into v1, right, v in or v in. Okay, so now I will convert this circuit, I will just convert this, like I have just shifted this voltage here, it is just a scale, right, it is just a positive scalar, because polarities I have already placed here, the polarities, because here plus was with the dot, so here also plus will be with the dot, polarities I have already taken care. So this will be the polarity, so this will be a AC source whose value will be n2 divided by n1 into v in. Okay, and here I have inductor. Okay, and current, their current is this I. Okay, and this is the instantaneous polarity, basically instantaneously this is plus, this is minus. Okay, so what will happen, basically my current will flow, my assumed actual current, because current, all this is load, right, this is inductor, right? It will take the current, it cannot generate the current by itself, it will take the current in AC circuit. So n2 by n1 into v in, so this is my reference current. Okay, so what I am observing is that I know the phase difference between this voltage and this inductor will be what? Between this voltage and inductor, the phase difference will be 90 degrees. So this I reference current or IL current, inductor current, or let me keep it I reference only, will lag the voltage by 90 degrees. So this is my instantaneous polarity, right? So this I reference, if my voltage is somewhere here, this is my required voltage N2 by N1 into Vin. So I reference will lag the voltage by 90 degrees. It is a pure inductive circuit. So my I reference will be here. Okay. What about I though? What about I? So I can see that if I apply KCL here, so I can observe the given current direction is negative of my actual current. So I reference plus I will be 0, right? So actually I is opposite of I reference. So I reference is here, I reference is here. So I will be opposite of I reference, so it will be here. Now can you tell me what will be the phase displacement, phase relation of the current I with respect to voltage? So this is just a scalar number, right? So this I can roughly write, I mean proportional to voltage only. Okay, N1 by N2 is just a positive scalar. So basically this angle will tell me the phase relationship between I and V in. So I can observe that I leads V in by 90 degree. So actually what is happening is that the phase relationship between the I and V in is leading. Although there is an inductive circuit here, but as the depending on the polarities, if let's say I would have swapped it, if the polarity was here, right? If the dot was here, if the dot was here, then answer would have been opposite. It would have been I lags the V in by 90 degrees. But as the dot is here, so now I, the given current, whatever given direction of current that they have given me, leads the V in voltage by 90 degrees. So these are all reference directions given to me. But actually internally I know that internally the inductor current will always lag the voltage by 90 degrees. That much I know. Okay. So internal inductor current is this I reference, but they have not asked me the phase relationship of I reference. They have asked me the phase relationship of I. So I will answer I only. Okay, whatever they have asked, I will answer that. You will not answer extra things, right? So if interviewer asks you to plot the voltage waveform of a RC circuit, you will plot the voltage waveform. If you will not, of course, plot, then start to plot the current waveform as well. If the interviewer asks you to plot the current waveform, you will plot it, right? You will not do extra things. So whatever is required, whatever is asked, that you will do, right? You will not say, sir, I know inductor current lags the voltage by 90 degrees, so I will tell that, yeah, I reference lags by 90 degrees. But that is not getting asked, right? They have asked I, so you will solve according to I. So these kind of questions are very easy, but 90% of the students will not be able to solve because they don't know how to start, because they have just mugged up the concept. What they have mugged up, that E1 by E2 equals to I1 I2 by I1 equals to N1 by N2. That is what they have done. That's it. Okay, they don't know these basic things. Okay, so trust me, whatever you are learning the best resource. So if I have enjoyed this lecture, make sure to comment down below regarding the feelings, and make sure to comment in the first video as well. And of course, don't forget to like the video. I will see you in the next lecture with more concepts of transformer about referred impedances. Thank you for watching, and I will see you in the next lecture. Until then, happy learning.